Okay, so thank you, everybody. I'm going to start with a short introduction to CROSS, a bit of our history. Then I'm going to be giving examples, some in the public domain and some through CROSS reports. And you're going to see quite a lot of pictures of things which have failed and disasters generally, which always provides interest. Now, it's a sobering thought, but every day somewhere in the world buildings collapse, and somewhere in the world there are major fires. But we can improve the situation by learning from experience, and we'll talk a bit about how we can do that. So the benefits are clearly set out, what we can do with the system we have. We make structures safer and ultimately save lives. But in the background to that, we can promote cultural change, we can identify shortfalls, we can improve competence, which is very important because we often find that competence is lacking. And we can assist with horizon scanning, which is looking beyond what is happening normally and see what might be the next big problem, might be the next big fire, might be a big structural collapse. But very importantly, being a part of the CROSS community protects your well-being, because anybody who's been associated with a major failure or disaster knows how terribly debilitating it can be. It can ruin lives, ruin careers, ruin firms. Very important to not be involved in a major collapse or catastrophe, and by being a member of the CROSS team, as I say, will help you do that. So the input to our system is that we get confidential reports to our website. We look at significant events in the public domain, and we get comments from our expert panel, and more of all of those in a few minutes. So we have a website. Anybody can link up to that. I hope all of you have, but if you haven't, do so afterwards. And everything on the website is free to use. We promote stuff through social media. We publish reports with expert commentary, and that commentary is designed so that the people reading the report and the commentary can avoid that sort of event in the future. We publish periodic newsletters, we publish occasional alerts, and we make presentations such as this. So there's quite a lot of output. It's all on the website. So here's some background. And these are just a few slides of major collapses in different parts of the world. This in Bangladesh was the worst man-made, man-induced building failure that we know of, which wasn't associated with some kind of terrorist or military activity. 1,200 people killed when the garment factory came down. In Nigeria, a lot of collapses. Fortunately, this one didn't injure many people, but we hear very little about them. But this is a classic pancake collapse of a nearly completed building, all folding down on itself. India is a place where there are many collapses, and again, not terribly much comes out of reasons for that. And in the UK, we've had two major events. One was back in the 1960s, which was Ronan Point building on the left here. We'll talk a little bit about that later. And then on the right, the Grenfell Tower, which was the tragic fire a few years ago, which killed 78 people in the UK. So we have had our share here of catastrophic building failures. And in the US, there has been the catastrophic failure of the Champlain Towers South building. And again, a bit more about that later. And we do have an international network of CROSS. The first group who joined were Australia, and then they were joined by New Zealand. So we've got CROSS-AUS, which is Australasia. We have got CROSS in the United States, which is very active. We hope the next organization to join CROSS will be the Proof Engineers Society from Germany. And there was a time led by Tony Smith, one of your stalwart members, when we looked at it for Southern Africa, but still some work to be done before that could be made to function fully. But there is an ambition, if the ambition exists on your side, to bring Southern Africa into the CROSS family. So here is the reporting process that we go through, and we'll start off with a timeline. So back in 1976, there had been a couple of failures. There had been some bridges, box girder bridges, which failed, and that was due to engineers not appreciating the fact that they were scaling up the construction of small bridges to much bigger ones. Owners wanted bigger spans, wanted cheaper bridges, and the flatness of the plates making up the webs of some bridges were not as flat as it was expected. So there was buckling. There were 2 or 3 major collapses. Then there was also Ronan Point, as mentioned, and at Ronan Point, this was a building constructed of precast panels, floor and wall panels, not very well connected together at all. They were kind of piled up, a bit like a house of cards. And up near the top, a lady one day decided she wanted a cup of tea. So she filled a kettle, and the buildings had gas in those days. She lit the gas, but something went wrong. There was a explosion, a relatively minor explosion, but the whole side of the building collapsed. Number of fatalities. And that was the first time the phrase disproportionate progressive collapse was used. So the Institution of Structural Engineers and the Institution of Civil Engineers formed SCOS, the Standing Committee on Structural Safety. And in 1995, HSE, which is a UK government department, Health and Safety Executive, joined in to support the work. And in 2005, they decided that there was a lot of stuff happening which wasn't necessarily reaching the press, reaching the headlines. So there should be a voluntary confidential reporting scheme launched. And that was when I came in. I joined to start a trial process, and I'm still here. But we used as a model a system called Aviation Safety Reporting System designed by NASA. And that's been very successful in the aviation world, and pilots, ground crew, staff, anybody associated with the aircraft industry can report stuff. And that's helped improve aircraft safety, which has aided any of us who have flown any time over the last 40 years. And in 2021, we expanded into fire safety following the Grenfell Tower fire. There have been 2 major investigations into that. One was by Dame Judith Hackett, and she produced an interim report into what might be done to prevent similar things happening in the future. The other one is an official government inquiry, which is still going on and will publish its results sometime next year. And that is what happened and why it happened. But Judith Hackett's report contained a recommendation that CROSS should be expanded into fire safety as well as structural safety. So we have support from the Institution of Fire Engineers, and we got some money from the government. So we launched in 2021 with fire safety in addition to structural safety. So what can be reported? And we're kind of a cradle to grave organization. We will take stuff at the design stage, the construction stage, and the operation stage, and at end of life. Now, most of the structural reports we get come in at design or construction, in fact, nearly 50% at construction. We don't get that many during the occupation phase because not many structural engineers are involved at that time. And we do get some about demolition going wrong. So here are some practical examples of that from CROSS reports. The top left is a small portion of a complicated finite element model of a very, very tall building. The green are vertical load-bearing elements. The red are transfer structures. And the concern here was from the reporter that they didn't really know what was going on. The load paths were so complex that they couldn't understand it. And in fact, we've had quite a lot of reports about things going wrong with computer-aided design and people not understanding what they were doing with finite elements. So the design phase. Moving down, see a highway bridge, and panels which had been bolted onto the side of the bridge, precast panels, were falling off. So that's something in use, and not something you want to be seeing when you're driving along this highway. In the middle, the top there was a tower crane which collapsed backwards, and up at the very top there was a 30-ton counterweight, and that passed through 6 floors of a building here without killing anybody. And the fault was the connection between the tower crane base and the pile cap underneath it. And there was the inappropriate use of resin anchors, which were not nearly good enough to carry the load from this crane. Both the designers and the contractors were prosecuted. Down below, a little bit difficult to make out, but these are rows of seats, the orangey, reddy color of seats. Down below here are panels, and somebody at an event in London, which was a rehearsal for the coronation, stood up, and as they stood up, the floor beneath them collapsed and they fell into the temporary structure below. And the reason it turned out was because lots of these stands had been stored during COVID, not been used, and some of the floor planks had rotted and nobody had noticed. And then on the right is a collapse during a demolition. And this was a large panel structure similar to Roland Point. And the demolition contractor was going to very, very gently knock it corner down, and then they touched the corner with a machine, and the whole lot came down in another progressive collapse. So we do get examples from start to the finish of the process. And a very important thing that we do is we look for precursors. There are the normal operations which happen on any project. Then moving up the triangle, there are concerns where something might have gone wrong, but there's no physical manifestation of that. Then we go to events. An event might be something which is on site, such as a physical failure of part of the structure. And then there are the big events, the fatalities. Now, nobody's going to come to us with those. They're going to go to the regulatory authorities first, although they may filter down to us in due course. But anything that happens within the green zone can be a precursor and can be reported to CROSS. And if we can spot the precursors, then we've got a good chance of avoiding more serious consequences in the future. So we have got an SRMS system, which is a complicated set of rules which abides behind the public face of our website. And here's how it works. Somebody will submit a report. And the process for doing that is very easy, and I want to encourage all of you to submit reports. That report goes to one of a very few number of people who are designated people, and they are authorized to see the reporter's name, but they then anonymize the report. The reporter's name and details are removed. Any identifying feature is removed, such as the name of a site or a product or the like. And then another attribute of designated people is they've got very bad memory, so they never remember in future who has submitted a report. So the anonymized reports will then go to the expert panel down here. The expert panel will review them, provide commentary, and those comments are edited, usually by a designated person. So out come the anonymized report with comments, and then it goes to a lawyer who reviews it to make sure that we're not going to fall foul of any legal processes, or particularly defamation cases we would worry about if something got identified or wrongly identified. It then goes back to the reporter to review, say, here's what we're going to say, do you agree with it? And reporters inevitably do. There's occasionally a comment comes back, but nothing very much. And then the report is published. It's published on the website, and certain ones are published in our newsletters. So then again, the big question is, so what? What has happened? Has that report made a difference? And we like to think it has, and we set out in our work to make sure that we can influence people. And over the years, we've developed an ethos of things which are associated with the CROSS brand. And all of those are very important to us. I'll just highlight a couple here. Authoritative. People know that when we say something, it is going to be correct. it is expert. So those two are connected together. We are independent of anybody, although we get some funding from various sources. We don't have a kind of editorial policy, which means that we have to pay attention to those sources. We're independent of everything. We never blame anybody. And one of the words which people, when they're asked about cross, and we had a public relations thing before we started the fire, what word you most associated with cross, and it was trusted. So all these are very important aspects of our ethos. And if you got involved in setting up one in Southern Africa, then you would get heavily involved in what those mean and how we function with them. And then our expert panel. These are just the structural panel. We have a separate fire panel, but people from all of those walks of life are on the panel. They are not selected because they are a contractor or because they are a regulator. They're selected because of their personal qualities. They will bring the ethos across, they will bring their expertise, and it's all voluntary. So we've got a very good range, but sometimes the range isn't big enough. We have to bring in others. We get a report which requires very specialist stuff, so we appoint visiting experts, and they will give advice on a particular specific and isolated perhaps event. So here are some examples. And one of these is in the public domain. There was a bridge collapsed in Florida in 2018. It was a precast two-deck assembly, which was going to be put onto supports at either end. And during the course of 3 weeks, after which it had been put in support, large cracks developed in it. So we published an alert in association with Cross US. And here are some details from the collapse. Now, these pictures we have used with permission, but they come from the official investigation by the American authorities. So on this very colourful picture on the left, you can see part of a truss, a vertical member coming down, horizontal member and a diagonal member, and they all meet at a very congested zone. Moving up to the top right here, you can see that node. And in fact, when the failure took place, there was jacking going on up here in the mistaken belief that increasing the tension in those cables would in fact cure the problem. It didn't, it made them collapse. So here are the cracks which are shown before that tensioning operation took place. And they're several inches deep. And these had been seen by, quite shockingly, the original designers, the people who had been checking the design, the contractor, the people who were checking the contractor, the local highways authority. And the point is that nobody had the ability, the desire, whatever, to say, we must stop what we're doing here, prop this thing and find out what's happening. So to which they said, right, well, we'll apply a bit more force and see what happens. And down it came. So the lesson learned there is if you see something which is defective, let people know. If somebody had said, we'll look at those cracks, that might have been a precursor, that would have been an event, but as it turned out, it was a catastrophic collapse with fatalities. Here's one which is a near miss. There are a number of schools in Edinburgh in Scotland, and what you can see here is a brickwork outer skin, and the white are insulation panels, and behind them is a blockwork wall infilling steel frame. And one day, in the aftermath of a hurricane which had crossed the Atlantic, there was quite strong winds, but not excessive. The gable end of this school building was sucked out, and 9 tons of masonry landed on a footpath. And that is another question of luck and timing, because a few hours later, there would have been young children and parents walking along there in the way into school. And that turned out to be a generic fault. It was found in quite a number of other school buildings. And it's surprising because there weren't the same designers for all these buildings, there weren't the same contractors, but they had not installed wall ties properly, they had not installed wind posts properly. So the result was there was nothing to stop these gable walls blowing out. Although only one blew out, 17 others were found to be defective and in need of repair. So the precursor was a safety one. Nobody was killed, but nevertheless they could have been. Here's one from America. This is a temporary stage structure, and we had published in Cross a couple of reports about much smaller temporary structures and the way they failed under wind load. And this is a big stage. If you can imagine this standing upright, it's got these fairly flimsy vertical connections. And what you can't see is from the top going diagonally down, there are cables attached to kentledges off frame. All the mass of this stuff is up at the top. It's like an inverted pendulum, and a relatively small wind attacked it, and it blew over, and again, multiple fatalities. And you can see the wind isn't terribly great because they've got ordinary tent structures here, which are surviving quite well. So, important lesson from this is that temporary structures, particularly those with lots of people in the vicinity, need to be treated very, very seriously, just as seriously as permanent structures. And here is a steel frame, and this is in London. And 15 days before the collapse, you can see what looks like a fairly ordinary frame, but there was a special feature to it, and that is the ground floor was going to be used for assembly purposes. So the ground floor had to be column free. So up at the top, there was a very big truss, downstand truss, and the intermediate floors were suspended from that by suspension hangers. And then one day, just after 40 people had left the site, another near miss, matter of luck and timing, the whole structure collapsed. And the reasoning was never fully fathomed out, but it was to do with tension members failing, and there were inadequacies in terms of design and in terms of construction. So lessons learned from that about paying attention to the way structures, particularly those without robustness, and if you've got tension structures, you tend not to have too much robustness, can fail. And here's one which has been hitting the headlines big time back in the UK, and this is reinforced autoclaved aerated concrete. I don't know if you've got any of this in Southern Africa, but it's a very weak form of concrete. And if you think in terms of compressive strength of concrete being around 30, the compressive strength of this stuff is around 3. It was used in the 1950s, 60s, 70s by buildings in the public domain, particularly schools and hospitals and other things on government estates. And we got a report to say that a plank had failed in the school roof. It come down in a classroom. So we produced a safety alert in 2018. And here's another one, a plank which had collapsed without warning. And here's the consequence. But this is a hospital which is propped. So quite often you go to a UK hospital now, you'll find some beams and some props holding up the area in which you are being looked after for whatever complaint you've got. And this is a quotation from the London Times in August, where a government minister said 34 buildings have concrete roofs in such a poor state they could collapse any minute. But the point is about this, and there have been 150 schools identified now in the UK and partly closed because of the problem. It is an excellent example, probably the best we've had for the use of cross. So we get a report in, we process that report, we publicize it, we get a few more reports in, we publish an alert. The alert is taken into account by government departments, but not quickly enough. So what we forecast in 2019 has come to pass big time in 2023. So I'm going to give you a couple of very simple examples to show you that not all cross stuff is at the high end and involves fatalities. But here was a model. What was required to be modeled was a concrete transfer structure with a masonry wall above it. So that should have been modeled as masonry wall, instead of which it was modeled as a solid wall. So it wasn't, the properties of masonry weren't given to it. So it was entirely different in its form of behaviour. What happened on site was that the transfer slab only had 50% of the required reinforcing, because of course the brickwork applies a load, particularly as that load is applied as the brickwork is laid, applies a load right along the beam, whereas a concrete, if that had been a concrete wall, it wouldn't have applied the load in the same way. And the solution had to be putting a steel beam in there. And then you can imagine the consequences for those involved in the design and the construction of that. And that was a very simple case. We've got another one, which might have been much worse, but wasn't. It's rather very representative. What the client required was they had a lump of soil here extending backwards, goodness knows how far, and there was a road surface on the top of it, and there was a handrail, and that was 1.8 meters high, and they wanted a retaining wall. The designer said, well, we'll use brickwork, and the computer model was entirely inappropriate. It was designed as fully fixed on three sides, despite the fact that at these 4.5 meter lengths, there was a movement joint, so there was no fixity at all. It was a cantilever, so it was not fixed at the bottom. The ground underneath here was poor quality. The designer had assumed there was a high bearing pressure allowance, and there would be horizontal loads on this railing above, and none of that was taken into account. Now, fortunately, this was spotted by a checker before it was built, but the checker had a real argument with the designer to show that this was an entirely inappropriate design. And if it had been built, it would undoubtedly have failed completely. And there have been quite a lot of cases of retaining walls failing and killing people when they did so. It is a slightly more light-hearted one, but we've had reports in of people stunt riding across the arches of bridges. And we've issued a warning to bridge designers to make sure that if you don't want this to happen, however exciting it might be for the riders, you should put some form of guard at the bottom of the arches to prevent people accessing them. But then, of course, on the aesthetic side, you've got a beautiful arch which comes down and melds beautifully with the road surface, and you don't want to put in spikes there to prevent the odd cyclist. And here's one that we published last week, and this is quite a significant one. We had two reports in of this type of failure over the years. And this is a roof beam system which was used in schools in the 1950s, maybe 60s. And there are plywood webs. There are wooden top and bottom booms, and it's covered with plywood cladding. And the whole thing sits on the end on a rather feeble end board arrangement, this being a wall, school wall. And two cases, these have failed. And it's not surprising after many years, because these were simply glued and nailed in place. It's a very unrobust form of structure. And here are some key points from it. It's potentially safety critical because it involves schools. The material, you might think, more appropriate to making some do-it-yourself household project. And two sudden collapses, either of which had been catastrophic had the buildings been occupied at the time. So again, precursors, and now we have issued an alert to government, whom we hope will circulate to all owners of schools to say whether you have got an old folded plate timber roof like this. So moving now on to fire reporting. The Great Fire of London in 1666 is famous, started apparently in a bakery, burned down most of London, but that was the start of fire safety within the UK. But mostly it developed over the centuries as a means of fighting fires rather than a means of protecting fires. And here's an example of a car park fire which was in Liverpool in the UK in 2017. And there was a 7-story car park. Fire started in one vehicle on the 3rd floor, spread rapidly vertically and horizontally. It's an open-sided car park, but it was made of concrete. So it's withstood the fire for several hours. but adjacent to the fire was a major arena, a hotel, and an apartment block. So the firefighters couldn't save the car park, but they protected the adjacent buildings from the effects of the fire. So inside, you could see that the thin concrete floors had collapsed, but the main structure, main reinforced concrete structure, was robust enough to withstand the fire, and it later had to be demolished. But it showed the robustness of a concrete frame in such a situation. But about 1,200 cars destroyed. This little image here is a drone which was used to go inside the very dangerous car park and make video film that it actually landed on the bonnet of the car, which was the original source of the fire, and took lots of videos of it. Now, we issued a safety alert on that and saying it's very rare to have multiple fires in a car park, but they can happen. And owners and occupiers and designers should be aware. And then 2 weeks ago, this is a steel frame structure at Luton Airport in the UK. It went on fire, 1,400 vehicles lost this time. And you can see steelwork has softened, steelwork has collapsed, and the whole of that is going to have to be demolished as well. And the interesting thing is, certainly in the UK, the regulations for open car parks are that they need 15 minutes of fire resistance, which is enough time for somebody in a car over here to get to a place of safety in a staircase tower there. Nevertheless, it doesn't protect the asset. So this building was designed and constructed after our alert on multiple story fires. And here's another one, a risk of collapse of CLT, cross-laminated timber structures. And this is coming at the very bottom of our risk pyramid. We haven't had much about fires in such buildings, but we have had an alert about it. We've published a report to industry saying, be careful about the fire risk of CLT in multi-story buildings. Something which is hit the headlines all around the world, of course, are safety risks of lithium-ion batteries. This is a test rig, and when you severely damage a car battery, a propulsion battery, then there is a jet of flame, much bit like a giant oxyacetylene flame, which comes out, and this can be 2 meters long or more. So if that happens in a car park, then it can very quickly ignite adjacent vehicles. And never mind the fire risk from the batteries themselves, all modern vehicles have got a high proportion of plastics in them, high proportion of rubber, high proportion of electronics. They're much more flammable than they used to be. So this is an ever-present and perhaps ever-increasing risk of fires in multi-story car parks. And of course, these would be worse if car parks had buildings above them, which is not the case in the two that we looked at. So collapses keep reoccurring. So we'll go back to the one we showed at the very beginning, and this is of the Surfside building in California. So it was 12 stories, collapsed progressively and almost instantaneously, but not quite. There were some precursors in terms of cracking, which had been observed some time before this collapse. It was reinforced concrete, so it was designed to the codes of 40 years ago, and may not have been designed as rigorously as we might do nowadays. There's an investigation ongoing by the National Institute of Standards and Technology in the States, and the two people leading that are in fact two of the leading board members of CROSS in the US. So we don't know what their deliberations are, but we'll be in a very good position to publicize the results when they come out next year. And those recommendations are going to have a profound effect on thinking about aging of concrete buildings everywhere in the world, because how do we know there aren't more similar buildings with collapse potential? So we're nearly finished now. Here are the key lessons which we can take from the reports which we've had and the public events which we've talked about. And the first one is that similar issues recur. So we see quite a lot of the same kind of thing. So we've got to keep giving the same messages. Communications and a lack of responsibility are very important, and particularly with modern methods of contracting, lots of different parties doing lots of different things, and everybody trying to shuffle responsibility off onto somebody else. Competency is lacking at every level, from the tops of boards of construction companies down to the people operating at all levels on site and in the design offices. We've got to worry about deterioration and degradation in older structures. For example, Surfside. Changes in architectural trends, and we will go back to the Grenfell fire, which was fueled by the flammable nature of the construction material which was put on the outside. Although it wasn't a load-bearing material, it was simply there to protect insulation, which had been put up to insulate the buildings and make it look pretty. Poor understanding of computer stuff, which we've talked about, and we're going to be producing in the not too distant future an alert on that. And we haven't seen many computer-aided disasters yet, although there was a huge one in the North Sea a few years ago when a vast concrete platform off Norway completely collapsed because the computer analysis was wrong. We haven't seen that associated with major buildings yet, but we will. There aren't enough structural engineers, certainly in the UK, or fire engineers, or in the States, because safety critical decisions are made by others. And go back to the very first example we looked about, the bridge in Florida. Safety critical decisions being made by people who didn't have the knowledge or authority to do so. For those of you in the design environment, pressure on fees. For those of you in the construction environment, pressure on costs. Poor supervision on site amounts to a lot of the reports we get. And then we've got the technical problems in addition to the human traits of carelessness, corruption, and ignorance. We have the 3 Ps affecting what we do. There are products, processes, and people. And people are the highest up on the list when it comes to the causation of what has gone wrong. So you can benefit your firm and your career by signing up. These slides will be, I understand, available, but if you happen to have a camera, you can scan that. That will take you to the Cross UK website. You can report there. You can sign up to Cross through that, and you will get newsletters from us, from the Australasians, or from the States. You will get our alerts. It's all free. And we very, very much want you to submit a Cross report. These reports are the oxygen on which we exist. And although in this presentation I've showed you some very high-profile disasters to raise awareness, there have been very simple reports, which are important reports, potentially life-saving reports, to do with computer modeling or designing a retaining wall or whatever. You can follow us on LinkedIn, and you can follow us on Twitter, although it's not called Twitter now, so we need to update that slide. So there you have it. Thank you very much for your attention, and we're open to discussion.